Tonight, we invite you to drift away from the noise of the day and turn your attention upward, past the ceiling, past the clouds, and into the silent machinery of the night sky. For generations, we have looked at the planets of our solar system, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and assumed they were the standard model for the universe. We believed that if we looked at other stars, we would find reflections of our own home. But as our telescopes have grown more powerful, a different and quieter truth has emerged. We are not the rule. We are the exception. Tonight, let us explore the beautiful, calm strangeness of where we live. Close your eyes and listen to a clock. Perhaps it is the small, battery-operated alarm on your bedside table, ticking away the seconds in the darkness. Perhaps it is the faint, rhythmic hum of the refrigerator in the kitchen down the hall. Or maybe it is just the steady, internal metronome of your own breathing. In and out, in and out. There is a comfort in regularity. We rely on the sun rising in the east and setting in the west. We rely on the moon waxing and waning, pulling the tides with a gentle, invisible hand. We rely on the seasons turning, spring into summer, autumn into winter. This predictability is the foundation of our sleep, our safety, and our sanity. When you look at a clock face, the numbers are always in the same place. The 12 is at the top. The 6 is at the bottom. The hands move in a circle, never speeding up, never slowing down. It is a system of perfect order. And for most of human history, this is exactly how we imagined our solar system. We saw the planets moving against the backdrop of the fixed stars, and we called them wanderers, but we knew their wandering was strictly disciplined. They moved in ellipses, governed by gravity, ticking around the sun like the gears of a vast, celestial timepiece. Imagine, for a moment, the model of the solar system you likely saw in school. A bright yellow bulb in the center representing the sun. Then, for small, rocky worlds huddled close to the warmth, Mercury, Venus, Earth, Mars. Then, a gap filled with asteroid rubble. And finally, the giants, Jupiter, Saturn, Uranus, Neptune, massive, gaseous, cold, and distant. Feels right, feels balanced. Small rocks near the fire, big gas giants out in the cold. It makes intuitive sense, doesn't it? It feels like the way things ought to be. Because this was the only solar system we knew, we naturally assumed it was the blueprint for all others. We assumed that if we traveled light years away to another star, a star perhaps very much like our sun, we would find a similar family. We expected to find small rocky planets hugging the star and big gas giants protecting the outer reaches. We expected order. We expected familiarity. This assumption brought us a sense of cosmic belonging. We were not just living in a random assortment of debris. We were living in a standard-issue solar system, a typical home in a typical neighborhood of the Milky Way galaxy. It is a comforting thought to carry with you as you drift toward sleep. The idea that our home is normal, that we are average, that the universe is repetitive and predictable. But the universe, in its quiet majesty, often defies our assumptions. What feels ordinary is often only familiar. What we take for granted as the standard model is simply the only view we have ever had from our own window. As you lie there, let your mind float upward, out of your room, above your roof. Picture the solar system as that clock again. The planets ticking in their lanes. Mercury, tick.
Venus, tic.
Earth, tick. It seems so permanent, so stable. But stability is not the same as normality. Tonight, we are going to gently peel back the curtain of this assumption. We are going to discover that this clock we live inside is unique. It is an antique, a rarity, a collector's item in a galaxy full of digital watches and strange timepieces we barely recognize. The rhythm of the night is steady, but the story of our home is not. We are living in a place that shouldn't, statistically speaking, exist in quite this way. And the realization of this fact doesn't bring fear. It brings a profound, hushed wonder. It makes the ground beneath your bed feel a little more precious, a little more fragile, and infinitely more special. Listen to the silence of the room. The air is still. The shadows are long. In this stillness, we can begin to appreciate the anomaly that is us. We are not the standard. We are the strange ones. And that strangeness is a beautiful thing to contemplate as the world slows down. Think of the word solar system for a moment. It feels like a universal term, doesn't it? Like ocean or mountain. We assume that when we say solar system, we are describing a category, a type of thing that exists in multiples across the cosmos. And we are. There are hundreds of billions of solar systems in our galaxy alone. But the architecture of ours, the specific arrangement of sizes, distances, and types of worlds, is turning out to be vanishingly rare. It is as if we looked up the word house in a dictionary and found a picture of our exact childhood home, down to the chipped paint on the mailbox and the crooked tree in the yard. For decades, we designed our textbooks and planetarium shows around the assumption that our layout was the template. We taught children that rocky planets stay close to the star, and gas giants drift far away. We said this with confidence because it was all we knew. It seemed logical. It seemed inevitable. But the universe does not owe us logic, and it certainly doesn't organize itself for our convenience. The universe is vast, creative, and endlessly experimental. And we are beginning to see that our particular experiment, the one that resulted in us, is an outlier. As you breathe slowly, in and out, consider this: every assumption you have ever made about what is normal in the cosmos may need gentle revision. Not because the data was wrong, but because the sample size was too small. We looked at one solar system and extrapolated 8 billion conclusions. It was the best we could do. But now, with thousands of other worlds cataloged, we can finally zoom out and see the full picture. And in that picture, we are a rare brushstroke, a color that doesn't appear often on the cosmic canvas. This realization should not unsettle you. Instead, let it settle into you like warmth from a blanket. You are living in a place that beat the odds. You are orbiting a star in a configuration that almost never happens. And yet here you are, breathing air, feeling gravity, watching the moon cross the sky. The improbability of your existence is not a reason for anxiety. It is an invitation to gratitude. What feels ordinary is often only familiar. And tonight, we are learning that even familiarity can be extraordinary when seen from the right distance. The crack in our assumption didn't happen with a loud bang. It happened with a whisper of data, a slight dimming of distant starlight that changed everything we thought we knew. For centuries, astronomers could only dream of seeing planets around other stars. The stars are so bright, and planets are so small and dim, that spotting them was like trying to see a moth flying next to a searchlight from miles away. But in the 1990s, and accelerating with the launch of the Kepler space telescope in 2009, we finally developed the technology to see. Kepler was designed to stare at a single patch of the sky, a field of stars in the constellations Cygnus and Lyra, without blinking. It watched over 150,000 stars simultaneously, waiting for the tiny, telltale dip in brightness that happens when a planet crosses in front of its star. A mini eclipse. We expected to find solar systems like ours. We prepared our models to categorize them. Earth-like planets here, Jupiter-like planets there. But as the data began to stream back to Earth, processed by computers and analyzed by scientists in quiet offices, a picture emerged that was confusing, then puzzling, and finally undeniable. The first things we found were impossible according to our standard clock model. We found gas giants, planets the size of Jupiter or larger, roaring around their stars in orbits of just a few days. Imagine Jupiter, not out in the freezing dark, but skimming the surface of the sun, closer than Mercury, roasting in temperatures of thousands of degrees. We called them hot Jupiters. They shouldn't have been there. Our theories said gas giants form far out, where ice can exist. Yet there they were, defying our rules. Then, as Kepler kept staring, it found something else. It found systems that were flat and packed tight like a stack of pancakes. Systems where 5 or 6 planets were crammed inside an orbit smaller than Mercury's. And strangest of all, these planets were often identical in size. If one planet was a certain size, its neighbor was likely the same size. They were like peas in a pod. Regular, uniform, rhythmic. The universe is calm, even when it is strange. This peas-in-a-pod architecture turned out to be incredibly common. Star after star showed this pattern. A family of planets that looked like siblings, evenly spaced, similar in height and weight. It was a harmony we hadn't anticipated. But then we looked back at our own solar system. We looked at our clock, and we realized something startling. We don't look like that. We are not peas in a pod. We are a mess of sizes. We have tiny Mercury, then Venus and Earth medium, then small Mars, then a huge gap, then massive Jupiter, then Saturn, then the ice giants. We are jagged. We are uneven. We are ordered in a way that implies a dramatic history, not a uniform formation. In 2023, a landmark study from the University of Bern quantified this feeling of isolation. Researchers Lokesh Mishra and Jan Alibert analyzed the architectures of hundreds of planetary systems. They categorized them into 4 distinct types. Similar systems where planets are like peas in a pod. Mixed systems where sizes vary randomly. Anti-ordered systems where planets get smaller as you go out. And ordered systems where planets get bigger as you go out. Our solar system is ordered. Small rocks inside, big giants outside. The study found that this specific architecture, the one we thought was the universal standard, is actually the rarest of them all. It appears in perhaps fewer than 20% of cases, and depending on how strictly you define it, we might be even more unique than that. Think about that as you settle deeper into your pillow. Out of every 10 windows you look into in the galaxy, 8 of them might show a family of identical planets huddled close to the fire. Only 1 or 2 might look like our home. We are the outliers. We are the vintage Victorian house in a neighborhood of modern, identical high-rises. This revelation is not frightening. It is awe-inspiring. It suggests that specific, perhaps chaotic events had to happen here to sculpt our system into this shape. The silence of space is not empty. It is full of variety. The universe is calm, even when it is strange. And we are living inside one of its rarest experiments. The Kepler data was so rich, so detailed, that astronomers began to see patterns they hadn't predicted. They saw that in many systems, if you plotted the planetary sizes on a graph, they would cluster tightly around a single value. The planets were not just similar, they were nearly identical. Imagine looking at a family and seeing quintuplets, not twins, not triplets, 5 children of the exact same height, weight, and build. That level of uniformity is striking, and it appears to be common. One such system is Kepler 11. It has 6 planets, all orbiting closer to their star than Mercury orbits our Sun. The planets range in size from twice Earth's diameter to 4 times. They are spaced evenly, like pearls on a string. When astronomers modeled the formation of such a system, they found that it required a very smooth, uniform disk of material around the star. No disruptions, no sudden events, just a slow, patient accumulation of dust into identical worlds. Our solar system shows no such patience. Our formation was violent, disrupted, and asymmetrical. We have planets that range from tiny Mercury, barely larger than our moon, to massive Jupiter, which could swallow over 1,300 Earths. This wild variation in size is not the norm. It is the exception, and exceptions, by definition, require explanations. As the 2023 Bern study showed, the key factor in determining what kind of system you get is the initial conditions of the protoplanetary disk. A low-mass disk with few heavy elements produces similar systems, the peas in a pod. A massive disk with abundant heavy elements produces ordered or anti-ordered systems, uneven, dramatic, and rare. Our Sun, it turns out, is slightly enriched in heavy elements compared to average stars. We are what astronomers call a metal-rich star, where metals means anything heavier than hydrogen and helium. This enrichment came from previous generations of stars that exploded as supernovae, seeding space with iron, silicon, carbon, oxygen, all the ingredients needed to build rocky planets and giant cores. So in a sense, we exist because of ancient violence. Stars that lived and died billions of years before our Sun was even a glimmer in a molecular cloud. Those stars forged the heavy atoms in their cores, then blasted them into space. That enriched material eventually collapsed into a new disk, and from that disk came the sun, and from the sun came us. We are made of stardust, not as a metaphor, but as a literal fact. And the specific mix of stardust we inherited made our system behave differently than most. Let that thought sit with you as you relax. You are not just on a rare planet. You are made of rare atoms, arranged in a rare configuration, orbiting in a rare architecture. Layer upon layer of improbability, and yet here you are, undeniably real. The universe is calm, even when it is strange, and your existence is proof that strangeness can be generative, creative, and ultimately nurturing. The discovery of our uniqueness didn't happen overnight. It accumulated slowly, data point by data point, year after year. Each new exoplanet discovery was like adding a single pixel to a massive image. At first, the image was blurry, meaningless. But as more pixels filled in, a picture emerged. And that picture didn't look like us. It looked like something else entirely. Compact, efficient, uniform, the galaxy's favorite design. And we were nowhere in that design. This moment of realization, when the scientific community collectively understood that we are the outliers, was not a single eureka moment. It was a gradual dawning, spread across conferences, papers, and quiet conversations in observatory control rooms. Astronomers would look at the data, then look at each other, and say, "Are we really that weird?" And the answer, increasingly, was yes. Yes, we are. And that's okay. In fact, it might be exactly why we're here to ask the question. Mathematics scribbled on a chalkboard? No. The proof is real, tangible, and intimately connected to the technology you use every day. The physics that allows us to find these distant worlds is the same physics that guides you to the grocery store. Consider the GPS on your phone. To tell you where you are, your phone listens to satellites orbiting high above the Earth. These satellites are moving fast, and because of their speed and their distance from Earth's gravity, time actually flows differently for them than it does for you. Engineers have to correct for these tiny relativistic effects, the bending of time and space predicted by Einstein, or the GPS would drift by kilometers every day. This exquisite sensitivity to motion and gravity is exactly what astronomers use to find exoplanets. When a planet orbits a star, it doesn't just circle the star. Gravity is a two-way street. The star pulls the planet, but the planet also pulls the star. They orbit a common center of gravity. This causes the star to wobble just a tiny bit. It moves toward us, then away from us. When the star moves toward us, its light waves get squashed, turning slightly bluer. When it moves away, the waves stretch out, turning slightly redder. This is the Doppler shift, the same effect that makes a siren sound higher pitch as it approaches you and lower as it drives away. By measuring these microscopic shifts in starlight, shifts smaller than the width of a human hair viewed from miles away, we can calculate the mass of the planet pulling on the star. We can prove it is there without ever seeing it directly. This is the radial velocity method. Combined with the transit method, watching the star dim as a planet passes in front, we have built a catalog of reality. The NASA Exoplanet Archive now lists over 5,900 confirmed worlds. This isn't a guess. It is a census. Every night, telescopes across the American Southwest and in orbit confirm this reality again and again. And what does this census tell us? It tells us about the super-Earth. In our survey of the galaxy, the most common type of planet we find is a world that is bigger than Earth but smaller than Neptune. A world between 2 and 10 times the mass of our home. We call them super-Earths or sub-Neptunes. They are everywhere. They orbit red dwarfs. They orbit sun-like stars. They are the standard citizen of the Milky Way galaxy. But look at our solar system. Look at our clock. We have Mercury, Venus, Earth, Mars. Then nothing. Then Jupiter. We have absolutely no planet in that size range. The most common planet in the galaxy is completely missing from our home. It is as if you walked into a house and found it had no kitchen. You would notice. You would wonder why. We also lack those hot Jupiters we talked about earlier. Our Jupiter is polite. It stays far away, orbiting every 12 years, not every 3 days. We lack the tightly packed inner planets. Our system is spacious, empty, and strangely devoid of the most popular planetary model in the cosmos. This proof is not distant. It is data that exists on servers right now. It is knowledge that has been confirmed by multiple missions: Kepler, K2, TESS, and now the James Webb Space Telescope. We are looking in the mirror and realizing our reflection doesn't match the crowd. We are something else. The universe is calm, even when it is strange. And perhaps our strangeness is exactly what allowed us to be here to think about it. If our solar system had been normal, packed with super-Earths, or dominated by a hot Jupiter, would Earth have survived? Would the stable, predictable rhythms of our tides and seasons exist? It is a question to hold gently in your mind as the night deepens. The technology that finds these distant worlds is the same technology that runs your life, often without you noticing. Your car's navigation system, the timestamp on your text messages, the synchronization of the power grid that keeps your lights on. All of these rely on precise measurements of time and space, measurements accurate to billionths of a second. And that same precision, when turned skyward, reveals the invisible dance of planets around distant suns. Consider for a moment the engineering marvel of GPS. There are 31 satellites in orbit right now, each carrying an atomic clock that ticks with near-perfect accuracy. These clocks are so sensitive that they can detect the fact that time moves slightly faster for them than it does for you on the ground. Why? Because gravity bends time. The deeper you are in a gravitational well, like the surface of Earth, the slower time flows. The satellites, high above, experience slightly less gravity, so their clocks tick faster. The difference is only about 38 microseconds per day, but over time, that would cause GPS to drift by miles. So engineers correct for it. They slow down the satellite clocks by exactly the right amount. This is general relativity turned into code, running on silicon chips in orbit. Now imagine applying that same sensitivity to the stars. When a planet orbits a star, the star doesn't stay perfectly still. Both the planet and the star orbit their common center of mass. For a massive planet like Jupiter, this center of mass might be just outside the surface of the star. For smaller planets, it's deep inside. But in both cases, the star wobbles. And that wobble can be measured. The light from a star is a wave, and like all waves, it has a frequency. When the star moves toward us, the waves bunch up, shifting toward the blue end of the spectrum. When it moves away, the waves stretch out, shifting toward the red. This is the Doppler effect, the same physics that makes a train whistle sound higher as it approaches and lower as it recedes. By measuring these tiny shifts, changes in wavelength smaller than a billionth of a meter, astronomers can calculate the speed of the star's wobble. And from that speed, they can infer the mass of the planet causing the wobble. The most sensitive spectrographs on Earth can detect velocity changes as small as 1 meter per second. That's walking speed. Imagine trying to measure the speed of someone walking on the surface of a star 10 light-years away, using only the color of the light it emits. It sounds impossible, but it's not. It's just difficult, and astronomers have gotten very good at it. The radial velocity method gave us our first confirmed exoplanets in the 1990s. 51 Pegasi b, discovered in 1995, was a hot Jupiter, half the mass of Jupiter, orbiting its star every 4 days. It shouldn't have existed. Theory said gas giants need to form far from the star, where it's cold enough for ice to exist. But there it was, roasting at 1,000 degrees Celsius, completing an orbit faster than a single week on Earth. This discovery shook the foundations of planetary science. If hot Jupiters exist, then planets can migrate. They can move. The solar system is not a static clockwork. It is a dynamic, evolving system, and our current configuration might not be the configuration we started with. The transit method, which Kepler used so effectively, is simpler in concept but just as profound. When a planet crosses in front of its star from our point of view, it blocks a tiny fraction of the star's light. For an Earth-sized planet transiting a Sun-like star, the dimming is about 0.01%, 1 part in 10,000. Kepler could detect this. It stared at stars for years, watching for that telltale repeated dimming. If the dimming happened on a regular schedule every few days, every few weeks, it was likely a planet. If it only happened once, it might have been a fluke or a different kind of event like a sunspot or a distant eclipsing binary star. By combining both methods, radial velocity and transits, astronomers can determine both the mass and the size of a planet. And from mass and size, they can calculate density. Density tells you what the planet is made of. A low density suggests a fluffy gas giant. A high density suggests rock and metal. An intermediate density might suggest water or a thick atmosphere or some combination. This is how we build a census of the galaxy. Not by visiting these worlds, but by watching their shadows and listening to the whispers of starlight. And what does this census tell us? Overwhelmingly, year after year. It tells us that super-Earths and sub-Neptunes are everywhere. They orbit red dwarfs, which are the most common type of star in the galaxy. They orbit orange dwarfs. They orbit sun-like yellow dwarfs. They are the default setting of planet formation. If you take a random star and look for planets, the most likely thing you'll find is a world 1.5 to 3 times the size of Earth, orbiting close to the star, completing a year in a matter of days or weeks. These are the citizens of the galaxy, and we have none. Our inner solar system is spacious, almost empty. Mercury, Venus, Earth, and Mars are spread out over a distance of $1.50. In many other systems, you could fit 5 or 6 planets in that same space. We have room to breathe, and that breathing room might be essential for life. If Earth had a massive sibling orbiting nearby, its gravity would perturb our orbit. Our climate might swing wildly between extremes. Our seasons might become unpredictable. The gentle, stable cycles that allowed life to evolve over billions of years might never have established themselves. So the absence of a super-Earth in our system is not just a curiosity. It might be a prerequisite for your existence. The universe is calm, even when it is strange. And sometimes that strangeness is the calm itself. The night is long and we have time. We don't need to rush. We are going to take a slow journey through this mystery together. We will walk the perimeter of our strange estate and look at the fences, the gaps, and the peculiar architecture that makes our solar system unique. Over the next while, as you relax into the warmth of your bed, we will visit 6 milestones of this mystery. We will gently uncover the story of our home, layer by layer. First, we will explore what exactly makes a solar system strange or normal. We will look at the blueprints the universe usually uses. Second, we will delve deeper into the mystery of the missing super-Earths. Where are they? Did we once have them? Third, we will follow the incredible journey of Jupiter. We will learn about the Grand Tack, a theory that suggests our giant protector was once a wanderer that almost destroyed everything before saving us. Fourth, we will look at the asteroid belt, that ring of rubble between Mars and Jupiter. We will see why it is surprisingly thin, a ghost of what it should be. Fifth, we will look at Mars, the red planet, our neighbor, and we will ask why it is so small. By all accounts, Mars should be bigger than Earth, but it isn't. Why? And finally, we will travel to the very edge of the darkness, far beyond Pluto, to look for the evidence of a ghost, Planet 9. A hypothetical world that might be lurking in the deep freeze, shepherding the flock of icy objects at the rim of our world. There is no test at the end of this. You do not need to memorize names or numbers. Just let the concepts wash over you like a slow tide. Let the vastness of the distances and the slowness of the timescales soothe you. We are talking about billions of years. We are talking about the slow, heavy dance of giants. There is nothing to do but listen and rest. As we embark on this journey, remember that the story of the solar system is not a simple narrative with a clear beginning, middle, and end. It is a layered history, written in the orbits of asteroids, the compositions of meteorites, the craters on the moon, and the simulations running on supercomputers. Each piece of evidence is like a word in a very long book, and we are still learning how to read the language. But the language is becoming clearer, and the story it tells is one of chaos giving way to order, of violence giving way to stability, of strangeness giving way to the familiar rhythms that allow life to persist. The 6 milestones we will visit are not arbitrary. They are the key inflection points in our solar system's biography. They are the moments when something dramatic happened or failed to happen, and the consequences echo down to the present day. Each milestone is a door we will open gently, step through, and then close behind us as we move to the next. There is no rush. The solar system has been here for 4.5 billion years. It will wait for us to understand it. First, we will define what strange means in a cosmic context. We will look at the architecture of planetary systems as a whole and see where we fit, or more accurately, where we don't fit in the grand catalog of worlds. We will learn the vocabulary that astronomers use to classify these systems, and we will see why our ordered configuration is so rare. This will ground us. It will give us the framework we need to understand everything that follows. Second, we will confront the mystery of the missing super-Earths head-on. We will ask, if these worlds are so common everywhere else, why are they absent here? Did they never form? Did they form and then disappear? Were they swallowed by the sun, ejected into interstellar space, or obliterated in collisions? The answer, as we will see, might lie in the migrations of the giant planets. The story of the super-Earths is the story of what Jupiter did and when and why. Third, we will follow Jupiter on its incredible journey, the Grand Tack. This hypothesis suggests that Jupiter didn't form where it is today, $5.20 from the Sun. It formed closer in, perhaps around $3.50, and then migrated inward, driven by interactions with the gas disk. It came as close as $1.50, closer than Mars is today, before reversing course and sailing back out to its current position. This journey reshaped the inner solar system, cleared out material, and may have prevented the formation of the very super-Earths we are missing. It is a story of a giant planet acting as both destroyer and protector, depending on where you stood. Fourth, we will examine the asteroid belt. This ring of rubble between Mars and Jupiter contains millions of rocks, but their total mass is surprisingly small, less than 5% of the Moon's mass. If you could gather every asteroid in the belt and press them together into a single body, you would get something smaller than Pluto. Why is the belt so depleted? Why isn't there a planet there? The answer, again, involves Jupiter. Its gravity has been stirring the asteroid belt for billions of years, preventing the rocks from coalescing, causing them to collide and shatter rather than merge. The asteroid belt is not a failed planet. It is a region where Jupiter made planet formation impossible. Fifth, we will look at Mars, our red neighbor. The fourth rock from the Sun. Mars is small, only about half the diameter of Earth and roughly 1/10 the mass. But simulations of planet formation almost always predict a Mars that is much larger, comparable to Earth or Venus. The real Mars is a Runt, a planetary embryo that never finished growing. Why? The Grand Tack offers an explanation. Jupiter's inward migration truncated the disk of material at about $1, starving the region beyond of the raw material needed to build a large planet. Mars formed from the scraps. It is a survivor, but it bears the scars of a violent past. And finally, we will travel to the outer darkness, beyond Neptune, beyond Pluto, to a region of space that is cold, silent, and largely unexplored. There, in the frozen wastes of the Kuiper Belt and the scattered disk, astronomers have found hints of a ghost, a massive, unseen planet that might be shepherding the orbits of distant icy objects. This is the Planet 9 hypothesis. If it exists, it would be a super-Earth exiled to the fringes of the solar system, orbiting so far out that it takes tens of thousands of years to complete a single lap around the Sun. It would solve the mystery of our missing super-Earth. We do have one, but it was kicked into the backyard, far from the warmth and light. Or perhaps it doesn't exist at all, and the orbital clustering is a statistical fluke. We will weigh the evidence calmly and see where it leads. Each of these milestones is connected. The story of the solar system is not a collection of isolated facts. It is a web of cause and effect, stretching across billions of years and billions of miles. Jupiter's migration affected Mars. Mars' small size affects the asteroid belt. The asteroid belt's depletion affects the rate of impacts on Earth. Everything is linked. And by tracing these links, we can begin to see the shape of the whole story. We can begin to see why we are here, in this rare configuration, under this quiet sky. So let us begin. Let your mind settle. Let your breathing slow. We are going on a journey through time and space, but we will do it gently, slowly, in a way that invites rest rather than tension. The universe is vast, but tonight, we only need to explore one small corner of it, our home. And that home, as we will see, is far stranger and more wonderful than we ever imagined. Let us begin by defining the architecture of home. When architects design a house, they have styles: Victorian, modern, colonial. The universe has styles for solar systems, too. The 2023 study from the University of Bern gave us the vocabulary to understand them. Imagine a family photo. In a similar system, the peas in a pod, all the children are the same height. They stand in a row, uniform and orderly. This is the most common photo in the galaxy's album. Roughly 80% of systems look like this. Then there are mixed systems, chaos, big planets next to small ones, random spacing, no discernible pattern. It's a candid shot where everyone is moving. Then anti-ordered. The big kids are in the front, close to the star, and the little ones are in the back. Imagine Jupiter orbiting where Mercury is, and Earth orbiting out where Pluto is. And finally, ordered, our family photo. The little kids, Mercury, Venus, Earth, Mars, are in the front. The giants, Jupiter, Saturn, are in the back. It looks organized to us, but statistically, it is the rarest arrangement. We are the odd family that lines up by height perfectly, in a galaxy where that almost never happens. Now, let's talk about those missing cousins, the super-Earths and sub-Neptunes. A super-Earth is defined as a rocky planet with a radius about 1.75 times that of Earth. A sub-Neptune is slightly larger, up to 3 times Earth's radius, likely with a thick, puffy atmosphere of hydrogen and helium. These worlds are the average outcome of planet formation. If you mix dust and gas around a star, physics usually bakes a super-Earth. So why don't we have one? To understand this, we have to look at how planets form. We start with a disk of dust and gas swirling around a baby star. This is the core accretion hypothesis. Dust grains bump into each other and stick. They become pebbles. Pebbles become boulders. Boulders become planetesimals, little planets. These planetesimals collide and merge to form full-sized planets. There is a crucial boundary line in this disk called the ice line or snow line. Think of a campfire on a cold night. Close to the fire, it's too hot for snow to exist. Water is vapor. But step back a few meters, and you reach a point where the air is cold enough for your breath to freeze. That is the snow line. In the solar system, inside the snow line, water was vapor. So the planets that formed there, Mercury, Venus, Earth, Mars, could only be built from rock and metal. Rock is rare compared to ice, so these planets stayed small. Outside the snow line, water froze into solid ice. Ice was abundant. It acted like glue. So the planets that formed there, Jupiter, Saturn, Uranus, Neptune, could grow huge, fast. They grew so big their gravity started sucking in the gas from the disk itself, ballooning them into giants. This explains the ordered structure to a point, but it doesn't explain the gap. Why is there such a huge difference between Earth and Uranus? Why nothing in the middle? And why is Mars so small? If it formed further out than Earth, shouldn't it have had more material? Professor Stephen Kane from the University of California, Riverside, performed a fascinating thought experiment. He ran a computer simulation where he dropped a super-Earth into the gap between Mars and Jupiter, right where it should be statistically. He wanted to see what would happen. The result was chaos. The gravity of this super-Earth destabilized everything. Tugged on Earth, it tugged on Mars. Over millions of years, the orbits became wild. In many simulations, Earth was ejected from the solar system entirely, flung out into the cold void. In others, Mercury and Venus collided. It seems that our peaceful, stable clockwork relies on that gap. We exist because the super-Earth does not. Our strangeness is our shield. The universe is calm, even when it is strange, and sometimes that strangeness is the only reason life can wake up in the morning. Let us pause here and consider the implications. If Stephen Kane's simulations are correct, and they are based on well-tested physics, then the architecture of our solar system is not just rare, it is fragile. It is balanced on a knife's edge. Add one element and the whole thing collapses. Remove one element and perhaps it collapses differently. We are living in a Goldilocks zone, not just in terms of distance from the sun, but in terms of planetary arrangement. Not too crowded, not too empty. Not too massive, not too puny. Just right. This fragility is humbling. It suggests that the conditions for life, or at least for long-term, stable, complex life, are even more specific than we thought. It's not enough to have a rocky planet in the habitable zone. You also need the right neighbors at the right distances with the right masses. You need Jupiter far away, not close. You need no super-Earths disrupting your orbit. You need a thin asteroid belt that occasionally delivers water and organic molecules, but not so thick that it delivers extinction-level impacts every million years. This is why the search for life beyond Earth is not just about finding Earth-like planets. It's about finding Earth-like systems. And those, as we are learning, are extraordinarily rare. Most planetary systems in the galaxy are compact, efficient, and uniform. They pack their worlds close to the star and make them all roughly the same size. It's an elegant design, but it might not be conducive to life. The gravitational interactions in such systems might be too intense. The climates might be too unstable. The delivery of water and volatiles might be too erratic or too violent. Our system, by contrast, is spacious, awkward, and asymmetrical. It looks like a rough draft, a first attempt, a system that barely survived its own formation. And yet, it is precisely this roughness that gave Earth the stability it needed. The universe is calm, even when it is strange. And sometimes, the calm is born from the aftermath of chaos. The core accretion hypothesis, which describes how planets form, is not a simple linear process. It is messy. It involves countless collisions, near misses, and gravitational tugs of war. In the early solar system, the region around the sun was filled with millions of planetesimals, rocky and icy bodies ranging in size from pebbles to small moons. These planetesimals crashed into each other. Sometimes they stuck together, growing larger. Sometimes they shattered, producing debris. Sometimes they were flung out of the solar system entirely by close encounters with larger bodies. Earth itself is the product of perhaps a dozen major collisions between planetesimals, each one lasting minutes but releasing more energy than all the nuclear weapons on Earth combined. The final major collision, roughly 4.5 billion years ago, was with a Mars-sized body that astronomers call Theia. This impact was so violent that it vaporized much of Earth's surface, ejected a massive amount of debris into orbit, and tilted Earth's axis to its current 23.5-degree angle. That debris eventually coalesced to form the Moon. So the Moon is not just a companion. It is a scar, a reminder of the violence that shaped our world. And yet, that violence was also creative. The Moon's gravity stabilizes Earth's axial tilt, which stabilizes our seasons. Without the Moon, Earth's tilt would wobble chaotically over millions of years, causing wild swings in climate. The Moon also drives the tides, which may have played a role in the origin of life by concentrating organic molecules in tidal pools. So the same event that nearly destroyed Earth also gave it the tools to become a cradle for life. The universe is calm, even when it is strange, and sometimes destruction and creation are two sides of the same coin. The ice line or snow line is another crucial element in understanding our architecture. In the early solar system, the sun was surrounded by a disk of gas and dust. Close to the sun, temperatures were too high for volatile compounds like water, methane, and ammonia to condense into solid form. They existed only as vapor. But beyond a certain distance, roughly 3 to 5 Australian dollars, depending on the exact temperature profile, the disk was cold enough for these compounds to freeze into ice. This boundary is the ice line. Inside the ice line, planets could only form from the relatively scarce rocky and metallic materials: silicates, iron, nickel. This limited their growth. Mercury, Venus, Earth, and Mars are made almost entirely of rock and metal, with only trace amounts of water and volatiles. Outside the ice line, planets had access to ice which was far more abundant. Ice acted as a glue, helping planetesimals stick together more easily. This allowed the cores of Jupiter, Saturn, Uranus, and Neptune to grow rapidly, reaching masses of 10 or 20 Earths. Once their cores were that massive, their gravity became strong enough to pull in the surrounding gas from the disk, hydrogen and helium, creating the thick atmospheres that define the giant planets. But here's the puzzle. The ice line should have been a smooth transition. There should have been planets on both sides of it, gradually increasing in size as you moved outward. Instead, we have a sharp discontinuity. We have Mars, small and rocky, at $1.50. Then nothing until Jupiter at $5.20. That gap is enormous. It's as if someone erased the middle pages of a book. And the most likely explanation for that erasure is Jupiter's migration. When Jupiter moved inward during the Grand Tack, it cleared out the material in that gap, scattering it inward toward the Sun or outward toward the asteroid belt. The gap is not natural. It is a scar left by Jupiter's journey. So when we look at our solar system, we are not looking at a pristine formation. We are looking at the aftermath of a major upheaval. We are looking at a system that was disrupted, reshuffled, and then allowed to settle into a new equilibrium. And that new equilibrium, by sheer chance, happens to include a small rocky planet at just the right distance from the Sun, with just the right neighbors, to allow liquid water to persist on its surface for billions of years. That is where you are tonight. That is the outcome of 4.5 billion years of chaos and calm, violence and patience, destruction and creation. What feels ordinary is often only familiar. Your room feels stable because you have lived in it for years. But zoom out and you are on a planet that is spinning at 1,000 miles per hour at the equator, orbiting the Sun at 67,000 miles per hour, in a solar system that is orbiting the center of the Milky Way galaxy at 500,000 miles per hour. You are in constant motion, held in place only by gravity, balanced on forces that are immense and invisible. And yet you feel still. You feel safe. That is the gift of scale. At the scale of your body, the chaos of the cosmos is smoothed out into a gentle, predictable rhythm. And tonight, as you drift toward sleep, you can rest in that rhythm, knowing that it has held for billions of years and will hold for billions more. Science is a story that is constantly being rewritten. We used to think the Earth was the center of the universe. Then we thought the Sun was the center. Then we thought our galaxy was the whole universe. Each time we learned we were smaller, but the universe was grander. The discovery of our solar system's uniqueness follows the same path of humility and wonder. Let's look at the specific chapters of discovery that brought us here. First, the Kepler mission, 2009 to 2018. This was the telescope that broke the dam. Before Kepler, we knew of a handful of exoplanets. Kepler found thousands. It stared unblinkingly at the Cygnus constellation and showed us the peas in a pod pattern. It showed us systems like Kepler 11 with 6 planets packed inside the orbit of Venus. Proved that nature loves tight, efficient packing. It showed us that super-Earths are the rule, not the exception. This was the first wake-up call. We looked at our spacious, empty inner solar system and realized, we are the weird ones. Second, the TESS mission, Transiting Exoplanet Survey Satellite, launched in 2018. TESS took the baton from Kepler and surveyed the entire sky, focusing on brighter, closer stars. TESS confirmed Kepler's findings but brought them closer to home. It showed that even around our nearest stellar neighbors, the standard architecture was different from ours. It solidified the statistical reality. The solar system model is not the galactic model. Third, the University of Bern study, 2023. We have mentioned this, but it deserves its place as a pivotal moment. Lokesh Mishra and his team didn't just observe, they classified. By running simulations of planet formation millions of times, they showed that the conditions required to create an ordered system like ours, small inside, big outside, are extremely specific. You need just the right massive disk, just the right amount of heavy elements, and just the right timing of the star's ignition. It's like baking a soufflé. If you open the oven door a second too soon, it collapses. Our solar system is a perfect soufflé in a galaxy of cookies. Fourth, the Stephen Kane simulations, 2020s. By using modern supercomputers to model orbital dynamics, Kane showed that our stability is fragile. He demonstrated that the missing planet, the super-Earth, isn't just missing by chance. Its absence is a structural load-bearing feature of our system. If it were there, we wouldn't be here. This experiment shifted our perspective from, "Where is it?" to "Thank goodness it's gone." These experiments didn't use test tubes or Bunsen burners. They used light from centuries ago and silicon chips from today. They translated numbers, tiny dips in light brightness, tiny shifts in wavelengths, into a map of reality. They told us that 5 Earth masses is enough to ruin a neighborhood. They told us that 0.1% of a star's wobble is a gas giant. They translated the language of the stars into a story we could understand. And the story is this: the universe tries many things. It builds systems that are crowded, systems that are hot, systems that are chaotic. But occasionally, rarely, it builds a system that is quiet, spaced out, ordered. A system with a small blue rock in the habitable zone, protected by a distant giant, free from the gravitational bullying of a super-Earth sibling. That is where we live. Each of these experiments, Kepler, TESS, the Burn study, the Kane simulations, represents a different way of asking the same fundamental question. How common is our solar system? And the answer, delivered with increasing confidence over the past 15 years, is not very common at all. In fact, rare might be too generous a word. Exceptional might be more accurate. The Kepler mission was a triumph of patience. Unlike previous telescopes that hopped from target to target, Kepler simply stared. It locked its gaze onto 150,000 stars and didn't blink for 4 years. This continuous monitoring was essential for detecting planets via the transit method. A planet transiting its star might dim the starlight by 0.01% for a few hours. If you're not watching at that exact moment, you miss it. And you need to see it happen multiple times, at least 3 transits, to confirm it's a planet and not some other phenomenon like a star spot or instrumental noise. So Kepler watched and waited and recorded every flicker of light. The data Kepler collected is still being analyzed today. Even after the spacecraft itself ran out of fuel and was retired in 2018, astronomers continue to find new planets in the archived data. They refine their algorithms, filter out noise, and extract signals that were too faint or too ambiguous to detect in the first pass. Each new discovery adds another data point to the census, and the pattern becomes clearer. Compact systems with similar-sized planets are the rule. Our spacious, asymmetrical system is the exception. TESS, launched in 2018, took a different approach. Instead of staring at one patch of sky, it surveys the entire sky, spending about a month on each sector. This allows it to find planets around brighter, closer stars, stars we can study in more detail with other instruments. TESS has already found thousands of planet candidates, many of which have been confirmed, and it continues to reinforce the lesson Kepler taught us. The galaxy is full of small, close-orbiting planets. Super-Earths and hot Neptunes dominate the population. Our inner solar system, by comparison, is practically deserted. The Burn study was different. It wasn't based on observations, but on simulations. The researchers used computers to model the formation of planetary systems millions of times, varying the initial conditions, disk mass, stellar composition, timing of events, and watching what emerged. This approach, called Monte Carlo simulation, allows scientists to explore a vast parameter space and see which outcomes are common and which are rare. The result was the 4-category classification we've discussed: similar, mixed, anti-ordered, and ordered. And the simulations showed that ordered systems like ours require a very specific set of conditions. Too much disk mass and you get mixed or anti-ordered. Too little and you get similar. The sweet spot that produces our architecture is narrow. This was not just an academic exercise. The researchers compared their simulations to real data from Kepler and TESS, and the match was good. The simulations predicted that similar systems should dominate, and they do. They predicted that ordered systems should be rare, and they are. This validation gives us confidence that the physics in the simulations is correct. And if the physics is correct, then the conclusions are sound. We are living in a statistically unlikely configuration. Stephen Kane's simulations were more targeted. He wanted to answer a specific question. What would happen if we added a super-Earth to our solar system? To do this, he used N-body simulations, which track the gravitational interactions between multiple objects over time. He placed a super-Earth at various locations between Venus and Earth, between Earth and Mars, between Mars and Jupiter, and ran the clock forward for 10 million years. In almost every scenario, chaos ensued. The super-Earth's gravity perturbed the orbits of the other planets, causing eccentricities to grow. In many runs, Earth's orbit became so elliptical that it either plunged into the Sun or was ejected into interstellar space. Venus and Mercury often collided. Mars was frequently kicked out of the system entirely. The only stable configurations were ones where the super-Earth was placed very far from the other planets, around $3 roughly where the asteroid belt is now. But even then, the system was more fragile than our current one. The results were stark. Our solar system stability depends on the absence of a super-Earth in the inner system. We are not missing a planet. We are missing a wrecking ball. These experiments, taken together, paint a coherent picture. They tell us that the universe is full of planetary systems, but most of them don't look like ours. They tell us that our architecture is rare, fragile, and dependent on a specific sequence of events in our distant past. They tell us that we are not the template, we are the outlier. And outliers, by definition, require special explanations. The beauty of this scientific process is that it is self-correcting. Every experiment invites scrutiny. Every simulation invites replication. If the results hold up under repeated testing, if different teams using different methods arrive at the same conclusions, then we can begin to trust them. And in this case, the results have held up. The message is clear and consistent. We are strange. And that strangeness is not an error or an artifact. It is a real feature of the universe. The universe is calm, even when it is strange, and our strange home is as real as the bed beneath you. To truly appreciate the calm of our home, we must visit the extremes. We must look at the wilder shores of the galaxy. Imagine a world like WASP-12b. This is a hot Jupiter. It orbits its star so closely that the star's gravity is pulling the planet into the shape of an egg. The atmosphere is being ripped away, consumed by the star. The temperature on the day side is over 4,000 degrees Fahrenheit. It rains molten glass, sideways, in winds that blow at 5,000 miles per hour. Or consider the TRAPPIST-1 system just 40 light-years away. It has 7 Earth-sized planets packed around a dim red dwarf star. All 7 could fit inside the orbit of Mercury. Standing on the surface of one, you would see the others hanging in the sky, huge and detailed, like moons. They are in resonance. For every 8 times the inner planet orbits, the outer one orbits 5 times, and so on. Perfect mathematical dance. It is beautiful, but it is alien. The radiation from the close star might strip away their atmospheres. The tides would be immense. Compared to these, Earth is a monastery. Our orbit is nearly circular. Our weather is driven by the sun, not by the gravity of a nearby sibling tearing at our crust. We have room to breathe. But how did we get this breathing room? The leading theory is a dramatic event called the Grand Tack. The hypothesis suggests that Jupiter didn't form where it is today. It formed closer in, maybe around $3.50 astronomical units. Then, driven by currents in the gas disk, it migrated inward. It sailed toward the sun, like a ship tacking into the wind. Jupiter plowed through the inner solar system, coming as close as Mars is today, $1.50. Its massive gravity acted like a snowplow, scattering the planetesimals that were trying to form there. Cleared the way. It disrupted the formation of any super-Earths that might have been growing. It starved Mars of material, keeping it small. Then Saturn migrated in behind it. Saturn's gravity caught Jupiter, and the two locked into a resonance. This interaction reversed their direction. They tacked and sailed back outward, moving to their current positions in the cold dark. They left behind a depleted, empty inner solar system with just enough material to form 4 small rocky worlds.
Mercury, Venus, Earth, Mars.
This grand tack explains so much. It explains why Mars is small, Jupiter ate its lunch. It explains why the asteroid belt is so thin, Jupiter scattered most of it. It explains why we have no super-Earths. Jupiter pushed the material into the sun. We are living in the wake of a giant's journey. We also see evidence of the late heavy bombardment, a period about 4 billion years ago when the inner planets were pummeled by asteroids. This likely happened when the giant planets shifted their orbits again later on, the NICE model instability, unsettling the remaining debris. The scars on the moon are the record of this time. But since then, silence. The giants stand guard. The debris is mostly gone. The clock ticks smoothly. The universe is calm, even when it is strange. Our calm is the result of a chaotic history. We are the survivors of a celestial renovation project that cleared out the clutter and left us with a clean, empty room to grow in. The Grand Tack is one of the most elegant and controversial hypotheses in planetary science. It explains so much: the small mass of Mars, the thin asteroid belt, the lack of super-Earths, even the delivery of water to Earth, that it feels almost too good to be true. And perhaps parts of it are. Science is always refining its models, and the Grand Tack will undoubtedly be modified as new data emerges. But the core idea that Jupiter migrated inward and then outward is supported by multiple lines of evidence. One piece of evidence comes from the asteroid belt itself. Asteroids are not all the same. They fall into different compositional groups based on their spectra, the colors of light they reflect. Some asteroids are rocky and dry, suggesting they formed in the inner solar system. Others are carbon-rich and icy, suggesting they formed beyond the ice line. The asteroid belt contains both types, thoroughly mixed together. This mixing is hard to explain unless something large moved through the belt, stirring it like a spoon in a cup of coffee. Jupiter, during its Grand Tack, would have done exactly that. Another piece of evidence comes from meteorites. Some meteorites that fall to Earth contain minerals that only form in the presence of liquid water. These are called aqueously altered meteorites. The water that altered them likely came from ice-rich bodies that formed beyond the ice line. But these meteorites are found mixed with dry, rocky meteorites from the inner system. Again, this mixing suggests a large-scale disruption early in solar system history. The Grand Tack provides a mechanism for that disruption. The late heavy bombardment is another clue. About 3.9 billion years ago, roughly 600 million years after the solar system formed, the inner planets experienced a sudden surge in impacts. We can see the evidence on the moon. The large, dark basins like the Sea of Tranquility and the Sea of Serenity were formed during this period. Earth would have been hit even harder, but plate tectonics and erosion have erased most of the craters. What caused this bombardment? The NICE model, named after the city in France where it was developed, proposes that the giant planet's orbits became unstable and migrated outward. This migration destabilized the outer asteroid belt and the Kuiper belt, sending a storm of icy bodies toward the inner solar system. The impacts delivered water, organic molecules, and energy, perhaps enough to sterilize Earth multiple times, or perhaps just enough to kickstart the chemistry that led to life. We don't know for certain, but we know it happened. The resonances in the outer solar system also tell a story. Neptune and Pluto are in a 3:2 resonance, meaning that for every 3 orbits Neptune completes, Pluto completes exactly 2. This resonance protects Pluto from close encounters with Neptune, even though their orbits cross. Resonances like this don't happen by accident. They are carved by orbital migration. When Neptune migrated outward, it captured Pluto and many other objects in resonances, like a net dragging through space. The fact that these resonances exist today is strong evidence that migration occurred. Jupiter's current position, $5.20 from the Sun, is also significant. It is far enough that its gravity doesn't destabilize the inner planets, but close enough that it can influence the asteroid belt and protect us from some long-period comets. If Jupiter had ended up too close, Earth might not have survived. If it had ended up too far, the delivery of water and volatiles to the inner system might have been too slow, leaving Earth dry. The fact that Jupiter is where it is, right in the sweet spot, might be pure luck. Or it might be a necessary condition for our existence, filtered by the anthropic principle. We find ourselves in a solar system with this architecture because only this architecture allows observers like us to exist. The TRAPPIST-1 system offers a fascinating contrast. All 7 of its planets are Earth-sized or smaller, orbiting a red dwarf star that is only 9% the mass of the Sun. The entire system is so compact that if you placed it in our solar system, all 7 planets would fit comfortably inside Mercury's orbit. The planets are in a chain of resonances, 1: 1.5: 2.4: 4: 6: 9: 15, meaning their orbital periods are related by simple fractions. This is a system that formed gently and has remained undisturbed. There was no grand tack, no giant planet migration. The planets formed where they are and stayed there. It is beautiful, efficient, and utterly alien. Standing on one of the TRAPPIST-1 planets, you would see the other worlds as large as the Moon appears from Earth. You could watch their phases change as they orbit. You could see weather patterns on their surfaces, assuming they have atmospheres. The gravitational tides would be immense, possibly locking the planets in synchronous rotation so that one side always faces the star and the other is in permanent darkness. The habitable zone in such a system is narrow, and the planets within it are constantly bathed in the flares and radiation that red dwarfs emit. Whether life could arise and persist in such an environment is an open question. But it is a question we can now ask because we know such systems exist. Compared to TRAPPIST-1, our system is vast and lonely. Mercury is $0 from the Sun. Neptune is $30. That is a factor of 75. In TRAPPIST-1, the outermost planet is only 6 cents from the star. The scale is completely different, and yet both are called planetary systems. Both are outcomes of the same fundamental process: the collapse of a gas cloud, the formation of a star, and the accretion of planets from the leftover disk. The universe uses the same ingredients: hydrogen, helium, dust, ice, but it bakes them into wildly different recipes. Our recipe is spacious, violent, and asymmetrical. It is the result of a giant planet moving in, then moving out, clearing the way, and leaving behind just enough material to form a few small rocky worlds. It is a recipe that almost destroyed us before we even existed. But it didn't, and now, 4.5 billion years later, we are here to look back and marvel at the chaos that created the calm. The universe is calm, even when it is strange, and our calm is a hard-won gift, purchased with the collisions of a billion planetesimals, the migrations of gas giants, and the patient work of gravity over eons. Tonight, as you lie in the stillness of your room, you are resting in the eye of an ancient storm. The storm has passed, the debris has settled, and all that remains is the gentle rhythm of a rare and precious world, turning in the darkness. Even with the grand Tack theory, mysteries remain. Paradoxes that keep astronomers awake at night, but which we can explore safely as we drift towards sleep. Paradox 1: the Mars problem. Simulations of planet formation almost always produce a Mars that is the same size as Earth or Venus. But real Mars is tiny, only about 10% the mass of Earth. It's a planetary runt. The Grand Tack offers a solution. Jupiter truncated the disk of material at $1, leaving nothing for Mars. It fits. It's elegant. But is it true? We see strong evidence in the simulations, but we cannot go back in time to watch. Paradox 2: the Great Gap. Why is there nothing between Mars and Jupiter? That is prime real estate. In other systems, that's where the super-Earths live. Here, it's just the asteroid belt, a collection of rocks that, if you rolled them all together, would make a ball smaller than our moon. It's a ghost town. Again, Jupiter is the prime suspect. Its gravity prevents the rocks from sticking together. It excites them, makes them collide and shatter rather than merge. Jupiter is the boss of the solar system. Nothing grows in its shadow without permission. Paradox 3: the shield or the sniper. For decades, we taught that Jupiter was our shield. Its massive gravity sucked up comets and asteroids that would otherwise hit Earth. We watched it happen in 1994 when comet Shoemaker-Levy 9 slammed into Jupiter with the force of millions of nuclear bombs. "Thank you, Jupiter," we said. But new simulations in the 2020s suggest a more complex reality. While Jupiter shields us from long-period comets from the deep freeze, it might actually destabilize asteroids closer to us, flinging them toward Earth. It might be a shield and a sniper, but the fact that we are here with a long history of life suggests the balance has tipped in our favor. Or perhaps Saturn helps to balance Jupiter's aggression. Paradox 4. The timing. When did the giants move? If they moved too early, they would have destroyed the disk before Earth formed. If they moved too late, the damage would have been different. The NICE model, named after the city in France, proposes an instability that happened hundreds of millions of years after the planets formed. This would explain the late heavy bombardment. It is a delicate choreography, a ballet of giants dancing on a stage of ice and rock. The resolutions to these paradoxes are likely found in the concept of resonance and conservation of angular momentum. The solar system is a closed system. Energy is not lost. It is traded. Jupiter trades energy with Saturn. They trade energy with the asteroid belt. The whole system breathes and flexes, seeking the lowest energy state, the most stable configuration. We are living in the result of that relaxation. We are the stable endpoint of a chaotic beginning. What feels ordinary is often only familiar. The stability of your floor, the quiet of your room, these are the local echoes of a gravitational stability achieved billions of years ago. We are safe because the giants finished their dance long before we arrived. These paradoxes are not problems. They are puzzles. And puzzles invite curiosity, not anxiety. As you lie there, consider how satisfying it is to know that there are still mysteries left to solve. The solar system is not a closed book. It is an ongoing investigation, with new clues emerging every year. Each meteorite that falls, each asteroid we visit, each simulation we run, adds another piece to the picture. And the picture, though incomplete, is becoming clearer. The Mars problem is particularly vexing because Mars is so accessible. We have sent dozens of spacecraft there. We have rovers on its surface right now, drilling into rocks, analyzing soil, searching for signs of ancient life. Mars is the most studied planet in the solar system after Earth. And yet, one of the most basic questions about it, why is it so small, remains only partially answered. The Grand Tack offers an explanation, but it is not the only explanation. Some researchers propose that Mars formed quickly, in the first few million years of the solar system, before the disk had time to deliver much material to its region. Others suggest that Mars was scattered outward from a closer orbit by gravitational interactions with other embryos, leaving it in a material-poor zone. Still others propose that the region around $1.50 was simply never very dense to begin with, perhaps because of a gap in the disk carved by an early generation of planets that were later destroyed or ejected. Each of these hypotheses has strengths and weaknesses. The Grand Tack explains not only Mars' small size, but also the asteroid belt's depletion and the lack of super-Earths. But it requires Jupiter to migrate at exactly the right time and reverse course at exactly the right distance. The early formation hypothesis is simpler but doesn't explain the asteroid belt. The scattering hypothesis requires specific initial conditions that may not be realistic. Science is the process of weighing these alternatives, testing their predictions, and seeing which one best fits the full range of evidence. We are still in that process. The answer may be a combination of several factors, rather than a single clean explanation. The Great Gap, the region between Mars and Jupiter where no planet exists, is equally mysterious. In other solar systems, this is prime real estate. It is the region where super-Earths love to form. It is inside the ice line but far enough from the star to have accumulated plenty of material. It should be the most populous part of the solar system, and yet it is empty, save for the thin scattering of asteroids. Jupiter's gravity is the obvious culprit, but the details matter. How exactly does Jupiter prevent a planet from forming there? The answer lies in resonances and eccentricities. Jupiter's gravity doesn't pull uniformly on the asteroid belt. At certain distances, called resonant orbits, an asteroid will complete an integer fraction of orbits for every one of Jupiter's orbits. For example, at the 3:1 resonance, an asteroid completes 3 orbits for every one of Jupiter's. At these resonances, the asteroid receives a repeated gravitational tug from Jupiter at the same point in its orbit. Over time, these tugs add up, increasing the asteroid's orbital eccentricity. Eventually, the eccentricity grows so large that the asteroid crosses the orbit of Mars or Earth, where it either collides with one of those planets or gets ejected by their gravity. This process, called resonant pumping, has carved gaps in the asteroid belt called Kirkwood gaps, named after the 19th century astronomer who first noticed them. These gaps are like missing teeth in the belt structure. They are evidence of Jupiter's long-term influence. But Jupiter does more than create gaps. It also prevents the asteroids from sticking together when they collide. At the velocities imposed by Jupiter's stirring, collisions between asteroids are too violent to result in merging. Instead, they shatter both bodies, creating more small fragments. This is why the asteroid belt is a belt of rubble rather than a planet. Jupiter made sure that nothing could grow there. The question of whether Jupiter is a shield or a sniper is more nuanced than it first appears. The traditional view was that Jupiter's gravity acts like a vacuum cleaner, sweeping up comets from the outer solar system before they can threaten Earth. And there is truth to this. Jupiter has a huge gravitational cross-section. Any comet that passes near it is likely to be deflected, captured, or destroyed. We saw this dramatically in 1994 when comet Shoemaker-Levy 9 broke apart and crashed into Jupiter over the course of a week. The impacts left dark scars on Jupiter's atmosphere the size of Earth. If that comet had hit Earth instead, it would have been an extinction-level event. But recent simulations suggest a more complicated picture. While Jupiter does protect us from long-period comets, those coming from the Oort cloud, far beyond Pluto, it may actually increase the rate of impacts from short-period comets and asteroids. Jupiter's gravity can kick objects from the asteroid belt or the Kuiper belt into Earth-crossing orbits. So it both gives and takes. It is a shield against some threats and a sniper aiming others at us. The net effect over billions of years appears to be slightly protective. But it is not a perfect shield. Impacts still happen. The dinosaurs can attest to that. The timing paradox, when did the giants move, is central to understanding the solar system's history. If the Grand Tack happened very early, within the first few million years, then it occurred while the gas disk was still present. This is important because the gas disk provides damping. It can slow down and circularize the orbits of planets that are becoming eccentric. Without the disk, migrations are more violent and less predictable. If the Grand Tack happened later, after the gas had dissipated, then the dynamics would be different, and the end state might not match what we observe. The NICE model, which describes a later instability among the giant planets, adds another layer. It proposes that Jupiter, Saturn, Uranus, and Neptune were initially in a more compact configuration, with more circular orbits. Then, hundreds of millions of years after formation, something triggered an instability. The planets' orbits became chaotic. Saturn, Uranus, and Neptune migrated outward. Jupiter migrated slightly inward. This reshuffling scattered the objects in the Kuiper belt and the outer asteroid belt, sending a storm of impacts toward the inner solar system, the Late Heavy Bombardment. This model is well supported by the evidence, but it raises the question: can both the Grand Tack and the NICE model instability have happened? Or is one of them wrong? The current consensus is that both likely happened, but at different times. The Grand Tack was early, during the gas disk phase. The NICE model instability was late, after the gas had dissipated. The two events are complementary, not contradictory. Together, they paint a picture of a solar system that was repeatedly disrupted and reshaped, rather than forming smoothly and staying static. This is a humbling realization. The solar system is not a clock that was wound up and left to tick. It is a dynamic, evolving system that has experienced multiple epochs of chaos and calm. The concept of resonance is key to understanding much of this. A resonance is a situation where two orbiting bodies exert a regular, periodic influence on each other. This can either stabilize or destabilize orbits, depending on the specifics. The resonance between Neptune and Pluto is stabilizing. Keeps Pluto from ever getting too close to Neptune, even though their orbits cross. The resonances in the asteroid belt, by contrast, are destabilizing. They pump up eccentricities and clear out material. Resonances are like musical notes. In harmony, they create beauty and stability. In dissonance, they create chaos. The solar system is a symphony of both. Conservation of angular momentum is another fundamental principle at play. Angular momentum is a measure of how much spin a system has. In the solar system, the total angular momentum is constant, assuming no external forces. When Jupiter migrated inward, it had to give angular momentum to something else, perhaps the gas disk or other planets. When it migrated back outward, it had to gain angular momentum from somewhere. This trading of angular momentum is what allows migrations to happen. It is a cosmic bookkeeping system that must always balance. The paradoxes we've discussed are not failures of understanding. They are the growing pains of a young science. Planetary science, as a discipline, is less than a century old. Exoplanet science is less than 30 years old. We are still learning the rules. And every paradox we encounter teaches us something new about how nature works. The universe is calm, even when it is strange, and the strangeness is part of the lesson. As you settle deeper into your pillow, let these paradoxes wash over you. They are not problems to solve tonight. They are mysteries to appreciate. The fact that we can even ask these questions, why is Mars small, why is Jupiter where it is, what happened billions of years ago, is a testament to human curiosity and ingenuity. We are a species that looks at the sky and asks why. We are not content to simply exist, we want to understand. And that desire to understand is itself a kind of beauty, a kind of calm in the face of cosmic strangeness. And now we reach the edge, the place where the map says, "Here there be dragons," the frontier of our knowledge. We think we know the solar system, 8 planets, Sunday asteroids, comets, but there is a ghostly fingerprint on the outer edge that suggests we are missing a family member. This is the hypothesis of Planet 9. Astronomers Konstantin Batygin and Mike Brown at Caltech noticed something strange about the orbits of the most distant objects we have found, icy rocks far beyond Pluto, called transneptunian objects, TNOs. These objects, with names like Sedna and Goblin, are not orbiting randomly. Their orbits are clustered. They are all swinging out in the same direction, tilted at the same angle. The odds of this happening by chance are tiny, about 1 in 500. It looks like something is shepherding them, something massive. Batygin and Brown calculated that a planet with a mass of 5 to 10 Earths, a super-Earth, could explain this clustering. It would be orbiting way out there, perhaps 400 to 800 times further from the Sun than Earth is. Its year would be 10,000 to 20,000 Earth years long. It would be frozen, dark, and invisible to most telescopes. If Planet 9 exists, it would solve the mystery of our missing super-Earth. We do have one. It was just exiled. Maybe during the Grand Tack, Jupiter ejected a sibling. Maybe we are not so different from other systems after all. We just kicked our super-Earth into the backyard. We don't know for certain. We have not seen it. It is a mathematical ghost. Some suggest it might not be a planet, but a primordial black hole the size of a grapefruit. Highly speculative. Others think the clustering is just observational bias. We're only looking where it's easiest to look. But soon we might know. The Vera Rubin Observatory, coming online in Chile around 2025, will survey the entire southern sky every few nights. If Planet 9 is there, Vera Rubin should find it. It will be a faint, moving dot against the fixed stars. We also have questions at the other end of the scale. The James Webb Space Telescope, JWST, is currently staring at the atmospheres of super-Earths in other systems. The COMPASS program, led by Johanna Teskey, is analyzing these worlds to see what they are made of. Are they water worlds? Are they rocky? Do they have oxygen? Methane? If we find biosignatures there, signs of life, it will make our own isolation feel even more poignant. Are we alone in a crowded galaxy? Or is life everywhere, just in different forms? We stand at the edge of this knowledge calmly. We do not need to know the answers tonight. It is enough to know that there are still mysteries to solve. It is enough to know that the dark is not empty. It is full of potential, full of planets waiting to be found, full of history waiting to be written. The search for Planet 9 is one of the most exciting and frustrating endeavors in modern astronomy. Exciting because, if it exists, it would be a major planet in our own solar system, hiding in plain sight, or rather, hiding in plain darkness. Frustrating because, Despite years of searching, no one has seen it directly. All we have are the indirect clues, the peculiar orbits of distant objects that seem to be influenced by something massive and unseen. The evidence is statistical. Out of the roughly dozen known objects in the extreme outer solar system, those with orbits that take them more than 250 Australian dollars from the Sun, about half of them have orbits that are clustered in a specific way. Their perihelia, closest approach to the Sun, all point in roughly the same direction. Their orbits are all tilted at similar angles. This clustering is unlikely to be random. If you shuffle the orbits randomly, the chance of getting this level of clustering is less than 1 in 500. Something is shaping these orbits. Something is hurting them. Konstantin Batygin and Mike Brown ran thousands of simulations to see what kind of object could produce this effect. They found that a planet with a mass of 5 to 10 Earths, orbiting at a distance of 400 to 800 Australian dollars, on an elongated, eccentric orbit could do it. The planet's gravity would not pull the objects directly. Instead, it would exert a slow, subtle torque on their orbits over millions of years, gradually herding them into the observed configuration. This is called secular perturbation, and it is a common mechanism in celestial mechanics. If Planet 9 exists, it would be a super-Earth, exactly the type of planet we are missing from the inner solar system. This has led to speculation that Planet 9 was once an inner planet, perhaps the fifth terrestrial planet, that was ejected during the violent early history of the solar system. Maybe during the Grand Tack, Jupiter's migration kicked a super-Earth outward, and it ended up in a distant, stable orbit. Or maybe it formed out there, from a particularly dense clump of material in the outer disk. We don't know. Both scenarios are plausible. The challenge is finding it. Planet 9, if it exists, is very far away and very dim. At 600 Australian dollars, it would be roughly 40 times farther from the Sun than Neptune. Sunlight falls off with the square of distance, so it would be receiving about 1,600 times less sunlight than Neptune. And it would be reflecting only a small fraction of that light back toward us. Even in the largest telescopes, it would appear as a faint dot, moving slowly against the background of stars. Distinguishing it from the millions of other faint dots in the sky, distant galaxies, asteroids, brown dwarfs, is a monumental task. The Vera Rubin Observatory, which began operations in 2024, is the best tool we have for this search. Rubin is designed to survey the entire sky every few nights, creating a time-lapse of the cosmos. Anything that moves, asteroids, comets, planets, will be detected. The observatory's camera is the largest ever built for astronomy, with 3.2 gigapixels, and it can image an area of sky the size of 40 full moons in a single exposure. Over the course of a decade, Rubin will generate the most detailed map of the outer solar system ever made. If Planet 9 is there, Rubin should find it. But there is also the possibility that Planet 9 doesn't exist. The clustering of orbits could be a statistical fluke, a result of observational bias. We tend to discover objects in the outer solar system during certain times of year, when certain parts of the sky are visible. This could create an artificial clustering that disappears when we find more objects. Some researchers have proposed alternative explanations for the clustering, such as a disk of small bodies collectively exerting a gravitational influence, rather than a single large planet. Others suggest that the clustering is real but caused by a primordial black hole, a tiny black hole with a mass of a few Earths, left over from the Big Bang. This idea is highly speculative and has little supporting evidence, but it is fun to think about. The search for life beyond Earth is another frontier, intimately connected to our understanding of planetary systems. The James Webb Space Telescope is currently observing the atmospheres of exoplanets, looking for molecules that might indicate life. Oxygen, methane, water vapor, ozone, these are biosignatures, chemicals that, in the right combination, suggest the presence of living organisms. JWST has the sensitivity to detect these molecules in the atmospheres of nearby super-Earths and sub-Neptunes. The COMPASS program, led by Johanna Teskey, is analyzing data from a dozen such worlds, trying to determine their compositions and assess their habitability. Early results are intriguing but inconclusive. Some super-Earths appear to have thick hydrogen atmospheres, like miniature Neptunes. Others appear to have lost their atmospheres entirely, stripped away by the intense radiation from their close orbiting stars. A few might have atmospheres rich in water vapor or carbon dioxide, suggesting they could be water worlds or rocky planets with substantial atmospheres. But none, so far, have shown clear biosignatures. That doesn't mean life isn't there. It just means we haven't found it yet. The search is just beginning. One of the challenges is that we don't know exactly what biosignatures to look for. Life on Earth produces oxygen through photosynthesis, but alien life might use different chemistry. It might produce methane or sulfur compounds or something we haven't thought of. The presence of a single molecule is not enough. We need to see a combination of molecules that are out of thermodynamic equilibrium. That is, that shouldn't coexist unless something is actively producing them. Oxygen and methane together, for example, would be a strong indicator, because those two gases react with each other and should disappear unless they are constantly replenished by biological or geological processes. The TRAPPIST-1 system is a prime target for these observations. 3 of its planets, TRAPPIST-1e, F, and G, are in the habitable zone, where liquid water could exist on the surface. They are also transiting planets, which means we can study their atmospheres by watching how they absorb starlight during transits. JWST has begun observing these worlds, and the data is being carefully analyzed. If we were to find biosignatures in the TRAPPIST-1 system, it would be a watershed moment in human history. It would mean that life is not unique to Earth. It would mean that our rare solar system, for all its uniqueness, is not the only place in the universe where biology has taken hold. But even if we don't find life in TRAPPIST-1 or any of the other nearby systems, it doesn't mean we are alone. The galaxy is vast. There are hundreds of billions of stars, and most of them have planets. The fact that we are searching at all, that we have the technology and the curiosity to ask these questions, is itself remarkable. We are the first generation of humans with the tools to search for life beyond Earth in a systematic scientific way. We are living at the dawn of a new era of exploration. The universe is calm, even when it is strange. And standing at this frontier, we do not need to be afraid of what we might find. Whether we find life or silence, planets or voids, the search itself is meaningful. It teaches us about our place in the cosmos. It humbles us, it inspires us, and it reminds us that we are part of something much larger than ourselves. A universe that is ancient, vast, and filled with wonders we are only beginning to understand. So as you lie there, drifting towards sleep, know that the frontier is still open. There are mysteries yet to solve, planets yet to find, and questions yet to answer. Planet 9 might be lurking in the darkness, waiting to be discovered. Or it might not exist at all, and the clustering of orbits might be a phantom. Super-Earths in distant systems might harbor life, or they might be barren wastelands. We don't know, but we are looking, we are searching, and that search is one of the most human things we do. The dark is not empty, it is full of potential, full of planets waiting to be found, full of stories waiting to be told. And tonight, as you rest in your rare solar system, you are part of that story. You are a witness to the unfolding of knowledge, the slow revelation of cosmic truth. The universe is calm, even when it is strange, and you are safe in its vastness, held by gravity, warmed by the sun, protected by the giants. Rest easy. The mysteries will keep until morning. If you find yourself returning to these cosmic questions night after night, you might enjoy subscribing to GravityWhisper. No pressure, just an invitation to join us in the quiet. Where are you listening from tonight? What city or state? What time is it in your part of the solar system? Leave a comment if you'd like to share. Sometimes it's comforting to know we're all under the same strange arrangement of planets, even as we drift towards sleep. Close your eyes once more. Can you hear the clock? Can you hear the steady rhythm of the night? Tick, tick, tick. We began by assuming that this ticking was the standard heartbeat of the universe. We end by knowing it is a rare and special syncopation. We live in the rarest type of solar system, an ordered architecture in a galaxy of similars. We are missing the most common type of planet, the super-Earth. We have a small Mars and a thin asteroid belt, scars from a time when Jupiter wandered like a lost ship in the night. Our home is a survivor. It is a unique antique, preserved by chance and gravity in a quiet corner of the Milky Way. The peas in a pod systems are common, yes, but maybe they are too crowded. Maybe they are too unstable. Maybe our specific strange arrangement, with its gaps and its giants and its small blue world, is exactly what was needed for you to be here tonight. What feels ordinary is often only familiar. Now you know that your familiarity is a gift. The stability of your bed, the air in your room, the gravity holding you down, these are not guaranteed. They are the result of a 4.5 billion year balancing act. The universe is calm, even when it is strange. Let that strangeness wrap around you like a blanket. You are safe in your rare solar system. The giants are far away, guarding the perimeter. The sun is steady. The earth is spinning, carrying you toward the morning. Our home is local, singular, and quietly extraordinary. There is no other place quite like it in all the catalogs of Kepler or TESS. We are the only ones with this specific view of the stars. Rest easy in your rare solar system. The stars will keep their secrets a little longer. Let the mysteries fade into dreams. You are exactly where you are meant to be. Good night from GravityWhisper. The clock is still ticking. Can you hear it? Perhaps it has slowed down now, its rhythm indistinguishable from the rhythm of your own breath. In and out, tick and tock. The machinery of the night is winding down, not because it is stopping, but because you are synchronizing with it. You are becoming part of the cosmic clockwork, a small but essential gear in the vast mechanism that turns the planets, swings the moons, and keeps the stars in their courses. We have traveled far tonight. We began with an assumption that our solar system was normal, typical, unremarkable. We ended with a revelation that our home is one of the rarest configurations in the galaxy. We are the outliers. We are the antique clock in a world of digital watches. And that rarity, that strangeness, is not a flaw. It is a feature. It is, perhaps, the very reason you are here to contemplate it. Think back to the beginning of our journey. We talked about the model solar system you might have seen in school. The sun in the center, the small rocky worlds huddled close, the gas giants far away. That model is correct, but it is also incomplete. It describes the structure we see, but it doesn't explain why that structure is so rare. Now you know. Now you understand that Jupiter's migration, the Grand Tack, cleared out the inner system. That Mars is small because it was starved of material. That the asteroid belt is thin because Jupiter prevented a planet from forming there. That we lack super-Earths because they either never formed or were pushed into the sun. Every gap, every oddity, every asymmetry in our solar system has a story. And those stories are stories of survival. Our home is a survivor. It survived the chaos of its own formation. It survived the migration of giants. It survived the late heavy bombardment. It survived billions of years of cosmic roulette, where a single wrong perturbation could have destabilized everything. And here it is, still turning, still stable, still nurturing life. You are the beneficiary of that survival. You are the inheritor of a 4.5 billion year legacy of fortunate accidents and improbable balances. The peas in a pod systems are common, yes. They are the galaxy's favorite design. They are efficient, compact, and uniform. But perhaps they are too efficient. Perhaps they are too compact. Perhaps the gravitational interactions in such systems are too intense for life to gain a foothold. Perhaps the climates are too variable, the orbits too unstable, the delivery of water too chaotic or too sparse. We don't know for certain, but we know that we are not like them. We know that our specific, strange arrangement has worked. It has produced a world where life arose, evolved, and eventually became capable of looking up at the stars and asking, why are we so strange? What feels ordinary is often only familiar. This mantra has echoed through our journey tonight. It is a reminder that your intuition about what is normal is based on a sample size of one. You have lived your entire life on Earth, in this solar system, under these conditions. So of course it feels normal to you, but zoom out and you see that normal is not what you thought. Normal is TRAPPIST-1, with its 7 worlds crammed into an orbit the size of Mercury's. Normal is Kepler-11, with its 6 planets orbiting in perfect harmony. Normal is the hot Jupiter, roasting in the heat of its star. We are not normal. We are exceptional. And that exceptionalism is a quiet, profound gift. The universe is calm, even when it is strange. This is our second mantra. It is a reassurance that strangeness does not imply danger. The universe is full of variety, full of experiments, full of structures that defy our expectations. But that variety is not chaos. It is creativity. It is the universe exploring the space of possibilities, trying every combination, every configuration, every permutation of matter and gravity and time. Most of those experiments fail. Most of those systems do not produce life. But some do. Ours did. And here you are, proof that strangeness can be generative, that the outliers can thrive, that the rare can become the real. Our home is local, singular, and quietly extraordinary. This is our third mantra. It is a celebration of particularity. Your home is not just any solar system. It is this solar system with this specific history, this specific configuration, this specific set of scars and gifts. There is no other place quite like it in all the catalogs of Kepler or TESS. The view of the stars from Earth is unique. The arrangement of our moons and planets is unique. The stability of our climate is unique. You are living in a one-of-a-kind place, and that should fill you with wonder, not anxiety. As you drift towards sleep, let these realizations settle into you like a warm blanket. You are safe in your rare solar system. The giants, Jupiter, Saturn, Uranus, Neptune, are far away, standing guard at the perimeter. They have finished their migrations. They have carved out their stable orbits. They will not wander again. The sun is steady, burning hydrogen in its core, fusing light and heat with a regularity that will last for billions of years more. The Earth is spinning, carrying you toward the morning, turning its face to the sun in a rhythm that has not changed for eons. You are held by gravity, warmed by starlight, protected by distance. You are exactly where you are meant to be. Think about the journey of light, the light that falls on your eyelids right now, whether from the moon or a street lamp or the faint glow of distant stars, has traveled across space to reach you. Sunlight bounced off the moon takes a little over a second to reach Earth. Light from the nearest stars takes years. Light from distant galaxies takes billions of years. You are seeing the past always. You are looking at a universe that is ancient, vast, and patient. And in that universe, you are a momentary flicker. But you are a real flicker. You are part of the story. And the story is still being written. Planet 9 might be out there, orbiting in the darkness, a ghost planet waiting to be found. Or it might not be. The answer will come in time. The Vera Rubin Observatory is searching. Astronomers are analyzing data. The truth is approaching slowly, one data point at a time. But tonight, you don't need to know the answer. You can rest in the uncertainty. You can let the mystery be a mystery. The universe does not require you to solve it. It only requires you to witness it. And you are doing that right now as you lie there in the stillness. The super-Earths in distant systems might harbor life. They might have oceans, continents, atmospheres, ecosystems. They might have beings looking up at their own skies, wondering if they are alone. Or they might be barren, lifeless, sterile. We don't know. JWST is looking. The COMPASS program is analyzing atmospheres. The data is accumulating. But the answer, if it comes, will come slowly. Science is patient. It does not rush. It builds knowledge one observation at a time, one experiment at a time, one insight at a time. And you are part of that process, even if you never step into a laboratory or look through a telescope. You are part of the species that asks these questions. You are part of the civilization that builds the tools to answer them. That is enough. The asteroid belt is still there, thin and scattered, a ghost of what it could have been. Jupiter's gravity still stirs it, preventing the rocks from coalescing, keeping the collisions violent and shattering. But that thinness is not a failure. It is a protection. If the asteroid belt were massive, if it contained hundreds of Earth masses instead of a fraction of one, the impact rate on Earth would be catastrophic. Life might never have had the time to evolve. The thinness of the belt is another gift, another lucky break, another part of the intricate balance that makes our home habitable. Mars is still small, still red, still a lonely outpost at the edge of the habitable zone. Its thin atmosphere, its frozen deserts, its ancient riverbeds. These are all evidence of a world that once had potential but never quite fulfilled it. Mars could have been Earth-sized. It could have held onto its atmosphere, kept its water liquid, developed a climate capable of supporting life. But Jupiter's migration starved it. Mars is a cautionary tale, a reminder that location and timing matter. But Mars is also still there, survived. It is a monument to resilience, a small world that refused to disappear, even when the odds were against it. Earth is still here, blue and green and alive, orbiting at just the right distance, tilted at just the right angle, spinning at just the right speed. It is a world that should not exist, statistically speaking. A world that required a specific sequence of events: Jupiter's migration, the moon-forming impact, the delivery of water, the stabilization of the climate, to become what it is. And yet here it is. And here you are, lying in a bed, breathing air, feeling gravity, thinking about the cosmos. You are the universe looking at itself. You are stardust contemplating its own origin. You are a rare thing on a rare planet in a rare solar system in a vast and ancient galaxy. And that is a beautiful thing to carry with you into sleep. The clock is still ticking, but you no longer need to count the seconds. You can let go of the need to measure, to quantify, to understand every detail. Some things are better appreciated than understood. The rarity of your home is one of those things. The strangeness of your solar system is one of those things. The improbability of your existence is one of those things. You don't need to solve them. You only need to rest in them, to let them hold you, to let them remind you that you are part of something far larger and older and stranger than you can fully comprehend. And that is okay. That is more than okay. That is exactly as it should be. Rest easy in your rare solar system. The stars will keep their secrets a little longer. The planets will continue their slow, patient orbits. The sun will rise in the morning, as it has for billions of years, as it will for billions more. You are safe. You are held. You are home. Let the mysteries fade into dreams. Let the vastness become a lullaby. Let the strangeness become a comfort. You are exactly where you are meant to be, in this moment, in this place, in this rare and precious corner of the cosmos. The universe is calm, even when it is strange, and you are part of that calm. You are part of that strangeness. You are a child of the stars, resting on a rare world, under a quiet sky, in a solar system that beat the odds. Good night. Good night from GravityWhisper. Sleep well in your extraordinary home.